determine function C in the time domain for a negative feedback controller with proportional only. Now our goal was to determine the advantages and disadvantages of different values of dip time, and we'll get to that after we determine C of T. This will work with any system with a proportional only controller. And here you have a block diagram, and from that block diagram with negative feedback control, we will determine the explosive transfer function, CLTF, and that's KC, this term right here, times this equation over 1 plus that numerator value. And we reduced it to this by multiplying times tau s plus 1 over tau s plus 4. To get into a polynomial, we use Padé's approximation here and put that in for e to the negative t naught s. Put it in there and also in the denominator, and then we multiply by 1 plus t naught over 2 times s on top and bottom to get this function, still the CLTF. And then if we have r of t is equal to 1, then r of s is equal to 1 over s. So we multiply essentially by 1 over s to get this equation for C of s. Using the final value theorem, the limit as s approaches 0 of s times the CLTF will give us a final steady state value. As you can tell, the s's will cancel out. Each of the s terms, the terms with s in them, go to 0, leaving us with kc over k on the top and 1 plus kck on the bottom, giving that as our final value. Now, to determine C of t, we will be taking the Laplace, the inverse Laplace, and so we need to simplify this denominator, and we'll be using partial fraction decomposition. So this is the characteristic equation that is just the denominator of C of s. To simplify our math, we will be calling the coefficient of the s squared term m, coefficient of the s term p, and the constant term q. That will give us just ms squared plus px plus q, and then we want a coefficient of 1 with the s squared term, so we divide by m, and then we're going to solve that, or set that equal to 0 to determine its roots. Again, there's the equation we have, and now we need to complete the square. So we'll take half of this, the s term, and square it, and add that to both sides. And now we use this with this equation, which is why we solve, and then subtract this q over m portion of the equation, and then carry through the squared term here, and then to get the same denominator here, we multiply this side times 4m over 4m. That gives us this s plus p over 2m squared plus p squared minus 4m cubed all over 4m squared. Now from there, we will be putting this equation in for that denominator. Remember, we took the characteristic equation and changed it to that. So we solve for 0 here, and I'm putting it down here. That s, we just multiplied by s, and then you'll see these will cancel. No, they won't. The numerator terms will cancel, but we still need to multiply this term by that entire numerator. That will give us this equation here, which we'll use to solve for a, b, and c. After simplifying this last term, see how it was there, and then we just simplified it to that. Then distribute the left side, so we will have a polynomial, and now we will solve for a, b, and c given these coefficients. We'll match up this. We'll start with the constant term, where c times q equals this constant term, kck. So that gives us c equals controller gain times the system gain all over that variable q that we determined. And then we will use the coefficients of the s squared terms to solve for a, and we already know c. c was kc times k over q, and then so a is to negative C times that M. And we will finally solve for B by plugging in A and C. And we will get this term where it's B is equal to the control gain times the system gain, all multiplied by the negative of the dead time over 2 minus P over 2Q. Now we will substitute for M, P, and Q again. Well, this is again to simplify our math. So this coefficient, called M, this coefficient P, and that constant term Q. And we plug those back into the terms for A, B, and C, for the equation for A, B, and C, to get these. Now we need to separate this equation because we were doing partial fraction decomposition. So we'll have just this A term over the denominator, B term over the denominator, and then this C over S term. And now we're going to manipulate our equation such that it matches the inverse Laplace, the given equations for Laplace from page 14. And these match. We have a constant term here, and then this matches the, I believe it's the sine term. Is that the cosine?
The cosine.
Yeah, one of these is the sine, the other is the cosine. And these are just constant terms, and C over S, we can easily solve the Laplace for that. So, by taking an inverse Laplace, we get this equation where there's a constant times this exponential term, cosine term, again, and then plus the constant term, another exponential term, and a sine term, and then a constant. Substituting back in all of our variables, A, B, C, M, P, and Q, we get this term for C of T. As you can tell, it's a lovely term. It's a very complex number. Again, with the final value theorem, where as T approaches infinity, these exponential terms go to 0. So this entire term goes to 0, this entire term goes to 0, leaving us with a final value of Kc times K over 1 plus Kc. You recall, that is also what we got when using the final value for the limit as S approaches 0 of S times C of S. Now our goal was to find the advantages and disadvantages of an increased dead time. And we determined from our C of T that increased dead time causes the system to reach a steady state faster, and it causes also larger values of steady state operating gain, and as we were told, bigger gain is better. And the disadvantages of increased dead time is that the ultimate gain of the loop is decreased. Smaller controller gain results in a larger offset and poor performance, as well as the limited values of operating gain. Are there any questions?
Yeah, can you go back over all the math again?
No, that's 9 then. Ha! Good job, 9 minutes. Oh, I wanted to say that.
Oh, man. Wednesday, Thursday, tomorrow? Sure? No? I sort of doubt it. I don't have it. I mean, I'm probably, I guess tonight I'll just do some stuff. I mean, I've done lots of presentations. I got 100 and 90. I'll be honest, you've already done 3, haven't you? Is it your turn? Did you do the last one? If you want to, man, you can do it, but I don't care. Like, I was just gonna throw some pods on there. I might even put my cat in it. I'm still I'm serious.
Each team will,
Now. Alright, so maybe I do what you
yeah.
What is this?
I mean, I did, in 14th now, purple has been merged with yellow.
Oh, really?
Who knows what's permanent, it's true today.
Okay.
Oh, we picked up, you merged with us now?
Yeah.
You got a presentation due tomorrow?
Well, this is tentative. The people in purple/yellow need to get together and decide if you want to be one team, or if you don't want to be one team, then decide something else to do. But now, look at these graphs. I wish this were in color.
I'm cool with it. I
but,
don't care.
there's a set point graph that I
Oh, crap.
believe